Hello everyone, welcome to Learn Overflow. In this video, we'll discuss about today's LeetCode problem, that is the kth smallest element in a sorted matrix. We'll understand what this question is all about, what this question is asking us to do, and what can be multiple approaches to solve this question, ultimately finding out what can be a better solution to solve this kind of question. Okay, so let's understand what this question is all about. Before moving on, make sure to subscribe to this channel for regular LeetCode videos like this. So first of all, this question is a medium level problem, and the question says we are given an n cross n matrix, so it's a square matrix, but that you can understand with that, and where each of the rows and columns is sorted in ascending order. Okay, so each of the rows and columns, everything. Okay, well, I'll show you what this exactly means after drawing a matrix for you. But remember that each of the rows and columns are sorted in ascending order. Okay, and after that we need to return the kth smallest element in the matrix. Okay, so we just need to return the kth smallest one, and further it says in a note that that it is the kth smallest element in the sorted order, not the kth distinct element. Okay, so why is it saying so? We'll understand from example as well. And it says you must find a solution with memory complexity better than n square. Okay, so it should be a memory complexity better than n square. All right, let's see what this question is asking. So there's a matrix given to us, 1, 5, and then 9. Let me just write this out. So there's a matrix for us, and that's the matrix being given to us over an example one. Okay, so that's being given to us. So what it first thing was, it says like each row and column is sorted in ascending order. So it means like, see, like each of the rows you can see there is sorted in ascending order. Each of the rows is sorted, and similarly, if you look at each of the columns is sorted in ascending order as well. So this you can see like each of the row and column are sorted in ascending order, right? So that's what they mean by that. And further, it also say that by k smallest element is the k in the sorted order, not in the distinct element. Why they mean so is that look, there are like different like same elements are also there in the matrix. Okay, 13 is being repeated, so it's not a distinct element, it's just the sorted order. Okay, so that's why in the first example the answer is 13, because that's being the eighth smallest element. Okay, so once we see this kind of question, what can be our approach? The first or the basic approach that we can have is like the brute force one is like have just traverse through all the elements and find the kth smallest element. What it mean is that say you just have a heap for you, okay, heap of size k, okay, that's the size of the heap you have, and you keep on adding each of the elements. So you keep go ahead with the n square loop. Okay, you go ahead with the n square loop and keep on adding each of the elements. First you add 1, then you add 5, then you add 9. Okay, similarly you keep on adding, say then you come across 10, then you come across 11, then you come across 13, and then you come across 12, which is smaller, so it could be like lower than this. Then you come across 13 again, and then you come across 15. So it is of size k. So size k is given to us as k as 8. So we'll just see 1, 2, 3, 4, 5, 6, 7, 8. So it's like 115 is added. It's the size goes beyond k, and you remove 15. Fine. So ultimately, after all the n square operations, going through the whole matrix continuously, you find out that okay, like you are left with k element in our heap. Fine. So that's what we are left with. Now, what can be done? And ultimately, we'll return. I'll simply pop the last element of the maximum element in the heap. So you will just find out that this is the answer that is asked for us. So there's 13 being returned to us. So that's the whole idea over here. Fine. So you can go ahead with a concept like this. You can definitely go ahead with that. But look carefully. You are going ahead with an n square operation. Fine. You are going ahead with an n square operation since you are traversing through the whole array or the whole matrix. Uh, the main thought is, can we improve this? When we say can we improve this, then remember definitely we can improve this. So the next improvement that we should look ahead is using a binary search. Okay, so binary search will be something like you have like you the whenever you know that this is sorted order. Okay, whenever it is say like is sorted, you can definitely think of using a binary search. Just think of this as a whole array and try to search the element. Like the you have the index. You rather you can know like you know the kth element. It is more like that, finding the minimum rotated subarray or those final duplicate number. Those are the binary search questions. So if you've done this question, you know that this can be done by binary search. Okay, so but I will not discuss much deeper in binary search in this video. Rather, I will go ahead with a much like with a better solution, a solution which will use a heap like this, but in that heap we will not traverse the n square. Okay, our traversal will not be n square. Rather, a traversal will be order of k. Okay, simply order of k, or you can say k minus 1 to be exact, but it's an order of k. So can we do that like that? What I mean is we are not traversing n square loop. Okay, it will be not a nested loop, but we'll go ahead with that. How we are thinking of that? Do something like use a tuple. Tuple in the sense you will store the I and j position of each element and the particular value, and use a min heap, like store a min heap based on that. Fine. Once you find a min heap, you will use a like once you have a min heap, you will find a solution based on. I will show you one by one. See, first in the tuple, we'll add the first row. Fine. So we'll simply add the first row. Okay, like I will build a min heap. That's the first row. How it will be? It will be something like first you will go ahead with 0, 0, like is a row column, and the value is 1. Fine. And we are checking the min heap based on the value. Okay. The next one we find is 0, 1, and 5. Fine. So this is a second value in our min heap. This is all added as a tuple. Okay, we'll just get another class called tuple and do on the best of that. It's not a big deal. I'll show you how you can do that. Next, you will add the next elements like 0, 2, and then 9. Fine. So these are the values you added. Now, once you have added the first row, the next one for next k minus 1 times, you will keep on doing a few operations. Operations like every time when you poll the min element, okay, you need to know the row number and the column number, which you can actually get from these values x and y in the tuple itself, and of the element, so that you can create a tuple and then replace that mean element that you found out with the next element of the same column. Okay, how is it so? See, exactly, our in our tuple, the mean element in the first place is 1, like 1. The value is 1, right? So we are just checking that's on the value. So mean element is 1, and we'll replace this with which element? We'll replace this with 1, 0 in the same column. Okay, the next element in the same column, like the getter element. So it was 0, 0. So we move to 1, 0. This position element. So 1, 0 being the row and column, and then what is the value? Value being 10. Fine, 10 given to us. Fine. So that's the value we have. Next, we have the mean element as 5. 5 is the mean element. So we pop that element, take that out of our mean heap, and then I replace that with the next element in the same column. So what's in the same column? 11 is the same column. So 0, 1 is the initial value. Now 1, 1 is the value over here. So row is 1, then 1 is the column, and this 11 is the value we have over here. Fine. Next, we come across this element 2, 9. We replace this, like we take it out and replace this with our like next column element. So we are not going through the whole n square loop. Rather, we are just changing these values, like changing this particular values we have over here. Fine. Next, we found 0, 2. So 0, 2 will just change it to 1, 2. 1, 2, and then we the value is 13. Fine. So that's the main heap we are creating. Fine. Next thing we'll go ahead with, we'll check for next value we find is 1, 0. Fine. So after 1, 0, we'll replace it with 1. Not 1, 0. That's like 2, 0. 2, then 0, then the value is 12. Okay. But like it's just a writing error, but look carefully. Once it's a heap and we are creating a min heap, then the values will be like 11 will be on top, then 12 will be in middle, and then 13 will be the value 13 will be at the last. So remember that operation. So the next element will be 11, that will be taken out. The next element will be taken out is 12, because the next smallest element is 12 and then 13. So I'm just writing it in this fashion, but keep that in mind that this is a min heap been going on. Okay. Next, so next we will just take out 11. So when we take out 11, we'll just increment this column, the next getter element in this column. So that will be like 2, and then 2, then 1. That's the column number, and then 13 being the value for us. Fine. The next one we'll take out is this one, because the next smallest element, like 13, 13, and 12, 12 being the smallest element. Okay, so we are using a min. That's what I say. So we take out 12, and then we find what exactly we find is like 12 is being taken out. So we find that we cannot move next to it. Fine. There's no greater value in this column. So we'll continue with that. We'll not check further, like we'll not try to add anything to that into our heap. Okay. The next one we'll take it out is like this element. It doesn't matter if you take out this element or this element, but like you may think it doesn't matter, but it does matter. Because why I'm taking out this particular element? Because when you're taking out 1 to 13, then actually we can check for this 15. Okay, but if we take out this 2 113, then again we cannot do anything, and we will end up having nothing in our loop. So this will be done internally, because the value added first will remain on the top, and same value that will be in the next position after that. So it is internally handled by the heap, so you don't need to think of that. But the next value will be taken out is this now, 1 2 and 13. For that, what we are doing, we'll just increment the x coordinate with x coordinate incremented. So it is like 2 2 and then 13. Fine. We just found that this is our value we have. Now after that, how many elements we actually popped? Check for that. We have 1 2 3 4 5 6 and 7. What is our k being given us to 8? So what I said, we'll pop a total of k minus 1. So that's what I said, take off k minus 1. Okay, we popped k minus 1 elements. Fine. After we pop k minus 1 element, now the next value we should pop is our answer, doesn't it? The next value we pop is like this one is the next value we can pop from our heap. So that will be our answer. So 13 is the answer, that's the one we should return. And that's our answer exactly. I'm sorry, I just said 13 here. This should be 15. Okay. This should be 15. Fine. So and see, that's how you come across this question. You're not going through like a n square loop, going through ij, everything. You're just going for this k number of terms. This can be beneficial if k is a smaller value. Okay, if k is like a greater value, no, I mean when k is a greater value, this is a beneficial time. But if k is a smaller value, then you need to remove it again and again and again. So we are just having three values in our heap. So you can see like the previous case, we are having k values in the heap. So it's like a higher complexity. So you are asked to do a solution with memory complexity better than n square. So if we are having key values in the heap, so in direct terms, indirectly what's happening? See, indirectly, if you look, the k can extend up to n square. Fine, k can extend up to n square, but for that case, it asks us to do like the space complexity or the memory complexity should be better than n square. Now, in this case, what we're doing, we are having at most three elements in our exact what is it, in our exact heap we have of the additional memory we're doing. We are having at most three elements, because we are removing the mini element and then adding an element based on that. So we are finding out a better than n square. Fine. So previously it was going up to n square, like k can be equal to n square, but now we are solving that issue. So that's the better solution, I think. Yes, you can definitely go ahead with the binary search solution, but even with binary search solution, you may not end up having a space complexity better than n square. Fine. Though you may argue that binary search is not using an enough space or multiple spaces, but there you are using mid. Okay, so it's more or less better, but I think this one is much better than the space complexity you have. Fine. So let's go ahead and write this code exactly on how we thought of this to work on. Fine. The first thing we should go ahead with defining a tuple for us. A tuple that will be helpful for us, like exactly how we define that. It should be a comparator should be there, and the comparator should work best on like a comparable variable, so that it should best on the value of the tuple. So that's the whole idea. So first we should define a tuple, and then we should go ahead with defining the whole code. The code is not much complex, so let's go ahead and do that. All right. So here you can see that this particular code actually works for us. So what exactly you will need, we will understand that. But this is 99 solution, but definitely you can improve this in further steps. Fine. So let's understand what exactly we try to do over here. Fine. The first thing is we implemented a class called tuple, and this class that we named as tuple, and just to implement a comparable. So what we have three variables: x coordinate, y coordinate, and then value. And that's the constructor we have for the tuple. And then for the we just implement the compare to method of the comparable class. So this is an override method. Fine. So we just need another tuple that there's a name of a tuple. Okay. So what is it? We just make it in a ascending order or in the mini format. Fine. So further, we just make sure that this is a mini format with the this minus that. Fine. So if we had done the reverse one, so that would be a maxi form. Now let's look for that. Uh, so in our main code, what we did, we just first took a length of the matrix. So we know the n cross n is our square matrix we have given at this n cross n. So we just found out the n from our matrix dot length. So that we got from there. Further, we just get a priority queue as a tuple being our variable, or the tuple being our particular queue is storing. Fine. Now here you can see the priority queue is not doing any kind of comparative anything, but why we are not mentioning it's in reverse order or in which order it should do, because we have already mentioned that if it's a tuple comparable comparative should be done in ascending order or in the mini format. So we just have mentioned this over here. So we don't need to do anything for additionally for this. Fine. Now, what exactly we did further? We just added a first row. So you can see it from 0 till less than n, and we just gave our x value being 0, and for the y value, we simply see this is x, this is y, and then we have val. So we simply keep I being the like all the first row we added in the tuple. Okay, like in the priority queue. All right. Then I added with that the value being the matrix 0 I. Fine. So that's the value we just added in our priority for like all the first row. Next, what we did, we just ran a loop from 0 till k minus 1. See, this is less than k minus 1. So this is like if there is like 8 elements, so we are just working for 7 elements. Fine. So 0 is still less than k minus 1. Now, further, what we're doing, we just pop the smallest element, the exact same thing that I was showing you of the few minutes earlier. I was showing you diagrammatically what we did. We just removed an element from the beginning and then did the further operation. So we just pop the first element, and further this line is like when we are coming to the at the bottom of the row. Okay, so we know that like the x row or the particular x row we have is already the n minus 1. So we don't have any further rows. So if we come across that step, we just continue. We just removed an element. Fine. The same thing which we did to remove the last row, like the last row element, like 12. We remember how we removed 12. We didn't add anything after 12. Fine. So if that is not the case, that this is not the end row, what we do, we just add elements to, like add a tuple to our priority queue. The tuple being t dot x plus 1. We just incremented the row number, keeping it in the same column. We just increment the row number, and we kept the column t dot y as same as it is, and we just changed the value being t dot x plus 1 or t dot y. So that's the matrix value we added. So that's the exact thing we just saw in the stack, and we just kept doing that in multiple steps. And after that, we did it exactly k minus 1 number of times. Fine. So now whichever element is in top of the queue we have is like the smallest one for us. Now, further, what we did, we simply return pico.pole. Pico.pole is written as a tuple for us, and then we made dot file. Dot file is the value we have for the particular tuple we have. So we simply return the value. Now, once we return the value, that's being our final answer we have. So that's how you saw the code works pretty good for us. That it works well. So that's the whole question is all about, and that's how we can actually solve it. Uh, I hope I can make you understand how you can solve the questions like this and how we should approach your questions like this. Okay. So yes, definitely, I will add a solution in the discuss section about the particular binary search method, but I will not suggest to go ahead with that, because I personally don't like if you have a question like this, like k smallest element. I know binary search is a good method, but you should think of finding solutions on this lines, on like using a priority queue or is a concept like this, because see, you hear your complexity, like your memory complexity is like, why is your memory complexity is going on? You know that k, if it's going from 0 to k, is like a space, it's not a space complexity, it's a time complexity is going on. But why is the space complexity going on is like, how many elements are there within your priority queue? How many elements are exactly there? It's like exactly n. It's not n square, okay? Because there are n elements that are going into your priority queue. It's not like n square elements are going into priority queue, right? You are just further what you are doing. You are just changing the column number, right? You are just increasing the not column number, keeping the column number same and increasing the row number. So you have only n elements. So you just improve this complexity. That's the question is specifically asking us to do, and that's the main target. So you should think on this line. That's what I felt. So this is the answer. If you have any doubts, make sure you just comment down in the comments below. I'll be happy to help you out as well. Also, like this video and share it with your friends who are solving to this difficult problem. Thank you all for watching this video. Hope to see you soon in my next video as well. Thank you.